Okay, so we're going to start the second half of the cardiopulmonary unit. Remember, there's 6 days that we're doing this, so this is day 4, by talking about gas exchange in the muscle. So we've got 5 outcomes that we're trying to get through here. And so we're going to start off with definitions. So to start off, we've got mixed venous and we've got arterial-venous oxygen difference. So mixed venous is just the amount of oxygen or the pressure of oxygen in the venous blood. Really, it's what's returning back to the right atria. You have to remember that not every tissue bed uses the same amount of oxygen. It depends on what's going on, what's active, what's less active, that sort of thing. So if you think about during exercise, the digestive tissues, the digestive system is going to be relatively inactive, at least from a metabolic standpoint. However, the muscles, on the other hand, are going to be highly active, and they're going to be pulling out a ton of oxygen. Digestive system, not so much. Okay, but it's not consistent. And so we've come up with this term called mixed venous, just saying, hey, what's back in the right atria so that when the right atria contracts, it mixes it all together. What's the pressure of oxygen? Then we have the arterial to venous oxygen difference. Okay, and so this gives us an idea of how much oxygen is a specific tissue bed using. Okay, and so the way we figure this out is we need to know the content in the arteries, we need to know the content in the veins, remember the equation we used last time, and that'll give us an idea of how much is actually being pulled out. Now on average, at rest, we're about 5 milliliters of oxygen per deciliter of blood. That's about 25% of the available oxygen. If you remember, typically we're about 20 milliliters of oxygen per deciliter of blood. However, when we get to exercise, and especially max exercise, that value triples. We get all the way up or close to 15 milliliters of oxygen per deciliter of blood. Now, when it comes to oxygen in the muscle, it's not enough just to get it into the muscle. We have to get it to the mitochondria. Okay, and so the way that this happens, and we've talked about this earlier in the term, we talked about this with our neuromuscular unit, is that myoglobin basically shuttles or transports oxygen to the mitochondria. Now, if you look at this equation here, or not this equation, excuse me, but this figure, you can see that myoglobin has a very high affinity or attraction for oxygen when compared to hemoglobin. So you just look here on the graph and just take a given value of pressure. Okay, so we're just going to say here around 35. Our saturation is about 50. Okay, but if we go all the way up to myoglobin, the saturation of myoglobin is almost at 90% when our partial pressure is 30. Okay, myoglobin only gets rid of oxygen when the partial pressure is very, very low. Okay, and so what really helps with this as well is that the partial pressure of an exercising muscle, the partial pressure of oxygen, is estimated to be about 1 millimeter of mercury. So very, very little. So this is a huge gradient, and it makes it easy for oxygen, or helps make it easier for oxygen to move. So this leads to the question, well, what determines the amount of oxygen that's taken up by muscle cells? Okay, and there are a couple of factors. One is how much oxygen is actually in the blood, how much blood flow is occurring, and there are some other things such as pH, temperature, carbon dioxide. Remember, we can shift the curve. Okay, the greater the oxygen content, the bigger gradient, it's going to make oxygen easier to be taken up by the muscle cell. The greater the blood flow, the more oxygen that's available. Same type of deal. Okay, but then like we've talked about in the past, if we've got high temperature, that makes it easier for oxygen to unload from the bloodstream, get into the tissues. If I have high CO2, same thing if I have a low pH or high acidity. Now, similarly, though, we want to get rid of carbon dioxide. And so as these muscles are working and using this oxygen, they're also producing a lot of carbon dioxide. Now, remember, the partial pressure of oxygen in the arteries is about 100. However, partial pressure of CO2 in the arteries is only about 40. Okay. However, there is a gradient, and so CO2 is able to diffuse out of the cell, okay, and into the bloodstream. It's transported to the lungs, and then we're able to exhale it and get rid of it. And so that's what we're done talking about for this one.